So next up, we have Raphael from EPFL. So Raphael is a PhD student at EPFL in their Sense Lab. He earned his MSc degree from the School of Computer and Communications Sciences at EPFL. Previously, he's worked as a research intern at Pavanos SARL, where he was hosted by Dan. He received his BSc degree at Politecnico di Torino from the Department of Electronic and Telecommunications as part of the Giovanni Talenti program. Raphael is also a huge user of srsRAN, and we are very, very happy that he was willing to travel all this way to give this talk. So yeah, please welcome Raphael.
Thank you, Brandon. I gotta switch the laptop, right?
Talk amongst yourselves while we quickly do this.
I can put it on. Well, thank you, Brennan. Thank you for the introduction for SRS. As Brennan said, my name is Raphael. Do we need a mic? Can everybody hear me? It's fine? Okay. Well, as Brennan said, my name is Raphael. I am part of the Sense Lab at EPFL, and today I'll talk about some work that my colleague and I have done on the latency of the srsRAN project. As you know, 5G is trying to cater for a very diverse set of applications, some of them requiring very low latency, like connected vehicles, remote surgery, remote gaming, augmented reality. For this, the 3GPP has introduced a new class of communication, the so-called ultra-reliable and low-latency communication, for which the specification call for very low uplink and downlink user plane latency as low as 0.5 millisecond. Now, these numbers are very low, and we've investigated the market, and it seems that even the big players like Nokia, Ericsson are still not able to achieve such low latencies. Nevertheless, since we've been using SRS for over a year, we decided to investigate the latency of the project and see if we were able to improve them in any way. So in here I report the downlink and uplink one-way latency of the srsRAN code base as you get it from GitHub, as you clone the repo. These measurements are done on band N78, as this is a common band for private 5G deployments across the world. So the usage of band 78 dictates for TDD, so time domain duplexing. Moreover, using band N78 in SRS also dictates the usage of numerology 1. So these measurements are taken with numerology 1 on band N78 with a very short TDD period. As you can see, the numbers are already very low, so we knew getting into this project that if we wanted to reduce the latency, squeezing every millisecond, every half a millisecond would count. And throughout this presentation, I'll show you how we were able to move from the distribution on the left to the one on the right, so decreasing the downlink one-way latency by 1.5 millisecond and the uplink one-way latency by 4 milliseconds. I'll do so by giving you a little bit of background. I'll then walk you through the latency analysis that we have undergone. I will tell you about the latency improvements that we have applied on the code base. I will give you a real-world evaluation, and I'll tell you about the next steps for this project. So let's start with the background. As you probably know, the 5G architecture is made of a radio access network and a core network. In this presentation, and since we have two things, I'll try to activate the pointer so both sides can see the pointer. In this presentation, I'll focus on the G0B component of the radio access network, and more specifically, I will focus on the SRS implementation of the G0B. Throughout the presentation, I will talk about uplink and downlink transmission, and I will refer to an uplink transmission for a transmission that originates from a UE and leaves the RAN, and I will talk about a downlink transmission for a transmission that generates outside the RAN and terminates in a UE. So, as Brandon said, the G0B is made of a central unit, a distributed unit, and a radio unit. And throughout this presentation, I'll focus on the DU and RU components. So I will talk about the RLC, MAC, and PHY layer, as well as the radio head. A key component, a key concept that's going to be needed throughout this presentation is the 5G frame structure. In 5G, 14 OFDM symbols are grouped into one time domain slot, whose length can vary, as 5G can support different subcarrier spacings. These subcarrier spacings are also referred to as numerologies. As I said, in this presentation, we will focus on band N78, which dictates the usage of numerology 1. So this gives us a time slot duration of 0.5 milliseconds. These slots are then grouped into subframes, which are subsequently grouped into radio frames. Now, with this little bit of background in mind, we can move to the latency analysis. Let me just. I will first start by talking about the latency in the radio unit. Then I'll talk about the latency in the distributed unit. Then I will talk about the latency introduced by the 5G protocol, and then I'll try to piece all of this together. So starting with the radio unit. Within the radio unit, we have two components, the lower PHY layer and the radio head. These two components are linked together by a software interface. In this presentation, I will focus on a USB-based software interface, as we've noticed that this is a very common setup for srsRAN users, just like the USRP B210 that Brandon just showed us how to use. Within the lower PHY layer, we have two processes. The downlink processor, who takes the downlink symbols from the upper layers and modulates them into downlink samples, which are then forwarded over the USB interface to the radio head. And the uplink processor, who receives uplink samples from the radio head via the software interface and forwards them to demodulates them and forwards the uplink symbols to the higher layers. So within the radio unit, we have three components. The downlink three processes, the downlink processor, the uplink processor, and the radio head. So let's see how they interact with each other. Let's try to follow a transmission. So let's say we are in a generic slot S. The radio head will receive the uplink signal from the air and will convert it into uplink samples. It will then forward these uplink samples to the uplink processor via the USB interface. So it will forward these uplink samples to the uplink processor, who will then demodulate them and convert them into uplink symbols. At the same time, the downlink processor is waiting. Once he receives the notification of the uplink processor that is done processing the uplink samples, it will start processing the downlink symbols for slot S plus H. These samples are then forwarded to the radio head, who will treat them after H slots. So we've introduced a H slot of offset between the downlink processor and the radio head. This H slot of offset between these two processes is needed for the downlink radio preparation time. This is needed for forwarding the downlink samples from the downlink processor all the way to the radio head, in order to allow the radio head to have all the samples ready to be transmitted when the time comes. This is needed because the samples have to traverse the SDR, so the FPGA, the RFIC, the modulator, and the amplifier. But more importantly, these samples have to traverse the USB interface between the host computer and the SDR. And this takes time. So we have measured the time that a batch of samples need, the amount of time that a batch of samples need to be forwarded from the host computer to the SDR over USB. And we have noticed that for some 30,000 samples, which are the samples needed to transmit a time domain slot in numerology 1, it takes over 250 microseconds. So this is the reason why we need an offset between the downlink processor and the radio head, because we need to allow these samples to reach the radio head and be ready when the time comes to be transmitted. Moving to the distributed unit. In here we have three components, so the RLC layer, the MAC layer, and the upper PHY layer. Within the distributed unit, there is the DU processor, who comprises the MAC layer and the upper PHY layer. This processor receives the downlink segments from the RLC layer, converts them into downlink symbols, and forwards them to the downlink processor. Conversely, in the uplink direction, it receives uplink symbols from the uplink processor and converts them into uplink segments that are forwarded to the RLC layer. Moreover, the MEC layer also is in charge of the real-time scheduling, so the resource allocation scheduling. So we've talked about the downlink processor. Now let's see how this, and the uplink processor. So now let's see how these two processes interact with the DU processor. Let's first look at the downlink transmission. So let's imagine the downlink processor has just finished processing the downlink symbols for slot S plus H minus 1. It will then notify the DU processor of the start of slot S plus H plus M. The DU processor will first decide on the downlink and uplink resource allocation, and then if this slot is a downlink slot, it will also prepare the downlink symbols to be transmitted. So in blue, I highlighted the time taken to prepare the downlink symbols. It will then forward these downlink symbols to the downlink processor, who will treat them after M slots. Again, we've introduced a slot between a higher layer and a lower layer that is needed as a buffer, as a margin, to allow the lower layer to have all the data ready once the time comes. Specifically, this M slot of offset is needed to handle any unexpected slowdown of the DU processor, allowing the downlink processor to run uninterrupted. Let me give you an example to better understand this. As I said, the DU processor prepares the symbols, which are then used by the downlink processor after M slots. The minimum value for M in SRS is 1, so let's say take the case of M equal to 1. For our first time, the DU processor has worked with no problem, so we prepared these samples and it has forwarded them to the downlink processor. But let's imagine the DU processor as an unexpected slowdown, so it is not able to produce the downlink symbols before the end of the slot. This does not cause any problem, as we have this margin, this M slot of offset between the DU processor. So the downlink processor had already received the symbols in advance and is able to run uninterrupted. Then, after the DU processor catches up, we are able to go back to a normal execution. And in all of this, the downlink processor has never stopped. So it has always had the downlink symbols needed to continue operating. So this is the reason why we need an M slot of offset between the DU processor and the downlink processor. In the other direction, in the uplink direction, once the uplink processor has finished processing the uplink samples, demodulating them into uplink symbols, it forwards them to the DU processor, who will treat them immediately. So to summarize these concepts that I understand are not trivial to grasp, we've created this slide in which we want to highlight the key idea of this analysis, that is, the higher layers always need to prepare the data in advance in order to allow the lower layers to have the data ready once the time will come. So we have introduced an M slot of offset between the DU processor and the downlink processor, and an H slot of offset between the downlink processor and the radio head. So we've talked about the latency introduced by the system implementation, so these H and M slots of offset. But we can also talk about the latency introduced by the 5G specifications. For example, once a UE wants to transmit some uplink data, it first has to signal to the G0B its intentions via a scheduling request. The GNB will then allow an uplink grant, and it will transmit it to a UE, which only then will be able to transmit the uplink data. Moreover, in TDD, slots are designated to be either uplink or downlink, so a UE cannot simply transmit a scheduling request or an uplink data whenever it wants, but it actually has to wait for the correct slot, so an uplink slot, to do so. Now, to better understand this and also to piece it together with the previous H and M slots offset, we've created an example. So in this figure, we report the radio head, the downlink processor, and the DU processor slots. And we have highlighted the uplink slots. So slots 3, 7, and 11 are uplink slots. So let's imagine a UE has some uplink data that it wants to transmit. It will first wait for the next uplink slot and transmit a scheduling request. So in slot 3, the G node B will receive the scheduling request. In the following slot, the DU processor will decode it, and after 2 slots, it will decide on an uplink grant. It will then prepare the downlink symbols, and it will forward them to the downlink processor, who after m slots of offset will start treating them. As I said, in SRS, the minimum value for m is 1 slot. So after 1 slot, the downlink processor will modulate the downlink symbols into downlink samples, thus creating the uplink grant. It will then forward these downlink samples to the radio head, who will treat them after h slots of offset. In SRS, h cannot be configured, and it's set to be 3 slots in numerology 1. After 3 slots, the radio head will then transmit the downlink samples over the air, and the UE will receive the grant, will demodulate the information, and will wait for the next uplink slot to transmit the uplink data, so slot 11. After that, the DU processor will demodulate the data. So with this little example, we can set some lower bounds for the downlink and uplink one-way latencies. And we can say that for the downlink one-way latency, we will need at least m plus h plus 1 slots, which translate into 2.5 milliseconds in numerology 1. And for the uplink one-way latency, we will need at least 9 slots in this configuration, which translate into 4.5 milliseconds. Okay, so I've introduced the latency that the analysis that we have undergone on the SRS stack. Now I would like to talk about the improvements that we have applied to the code base to reduce the latency. I will do so by introducing 3 modifications. Let me first recall that in SRS, the downlink processor always waits for the end of the uplink processor to start handling the downlink symbols. This can introduce extra latency, as these downlink symbols might already be ready at the beginning of the slot or even earlier. Moreover, let me also remind you that the h parameter in SRS is fixed and cannot be configured. So for our first modification, we allow the downlink processor to run at the beginning of the slot rather than waiting for the uplink processor to be done. Moreover, we also allow the h slot parameter to be configured in the configuration file. And by advancing the downlink processor from the end of the uplink processor to the beginning of the slot, we were able to reduce this h parameter from 3 to 1. So going back to our little example, as I said, in applying this modification, we were able to reduce the h parameter from 3 to 1, which allowed us to reduce the downlink one-way latency by 2 slots, so 1 millisecond in numerology 1. But this did not make any improvement in the uplink one-way latency, as the UE still needed to wait for the next uplink slot to transmit the data. So it still needed to wait for slot 11 to transmit the uplink data. So we still needed at least 9 slots to perform an uplink transmission. So for our second modification, we thought, what if instead of having the downlink processor run periodically at the beginning of every slot, what if the downlink processor could simply run event-driven by the DU processor? So whenever the DU processor would be done processing the downlink symbols, the downlink processor could immediately act on these downlink symbols, modulating them into downlink samples. In this way, we were able to eliminate the m slot of offset between the DU processor and the downlink processor. And going back to our example, as I said, we were able to, in this way, to reduce the m slot of offset from 1 to 0, further reducing the downlink one-way latency by another slot, so another 0.5 millisecond, leaving the lower bound for the downlink one-way latency to 1 millisecond. But more importantly, we were now able to catch the previous uplink slot for the uplink transmission. So we were able to cut down the uplink one-way latency by a TDD period, so 4 slots in this configuration, 2 milliseconds in numerology 1. Yet, the UE still needed to transmit a scheduling request in order to allow for to ask for an uplink grant before being able to send the uplink data. But what if the UE was able to send uplink data without asking for it in advance? So just transmitting the uplink data whenever it needed to. For this, we have implemented a scheduling request-free access mode. So an access mode in which the UE doesn't need to ask for uplink data, an uplink grant in advance. We did so by allocating a fixed amount of uplink resources to a UE, which enabled them to transmit uplink data whenever they needed to, instead of asking for it in advance. This modification did not make an improvement in the downlink one-way latency, as the scheduling request is not involved in the downlink transmission. So the lower bound for the downlink one-way latency remained 1 millisecond. But in this way, we were able to cut down the uplink one-way latency by another TDD period, so leaving us with only one slot of minimum uplink one-way latency, which translates into 0.5 millisecond in numerology 1. So I've now introduced the latency improvement that we have applied to the code base. Let me give you a real-world evaluation of our implementation to see how they really play out in the real world. For this, we have set up a testbed based on an Intel NUC with a 12th gen Intel Core processor, so a consumer CPU, which was running both the G-Node-B and the mobile core. So we used Kubernetes to orchestrate all of the microservices of the mobile core and the G-Node-B. We then used a USRP B210, so a USB-based software-defined radio as our radio head, and we used a Quectel 5G discrete modem as our UE. The modem was then connected to the same host via USB and was managed with the network manager. This allowed the creation of two interfaces, so a virtual interface for the G-Node-B and a network interface with the UE with the same time reference. This was key to perform a one-way latency measurement, since having the same time reference at both interfaces allowed us to timestamp ICMP packets that were flowing from the core to the UE, and by subtracting the timestamps, we were able to measure precisely the one-way latencies. Now, I've included here a picture of this testbed. It was really a simple testbed, so we used an Intel NUC, a USRP B210, and a Quectel discrete 5G modem. With this setup, we were able to measure the SRS latencies, and these are the latencies that you get out of the box, but just by cloning the repo from GitHub. As you can see, the downlink one-way latency spans from 3 to 4.5 milliseconds, and the uplink one-way latency spans from 6 to 8.5 milliseconds. So this value comply with the lower bounds that we've given during our evaluation. But you might wonder, why is there a gap between the lower bounds and the minimum of these distributions? The reason is that our analysis only included the G-Node-B side of the transmission. Unfortunately, the UE was completely closed source, so we had to treat it as a black box. Introducing our first modification, so allowing the downlink processor to run periodically at the beginning of the slot, allowed us to reduce the H slot of offset from 3 to 1, which allowed the downlink one-way latency to be reduced by 2 slots, so 1 millisecond in numerology 1. But this did not make any improvement in the uplink one-way latency, as the UE still needed to wait for the following uplink slot to transmit the uplink data. So moving to our second modification, which allowed us to also reduce the M slot offset from 1 to 0, it allowed us to further reduce the downlink one-way latency by another slot, so another 0.5 millisecond, leading the improvement to 1.5 millisecond. But more importantly, it allowed the UE to catch the previous uplink slot, so reducing the uplink slot one-way latency by 1 TDD period, so 2 milliseconds in this configuration. Then moving to our last modification, so the scheduling request-free access mode. As I said, the scheduling request is not involved in a downlink transmission, so the downlink one-way latency lower improvement was still 1.5 millisecond, but this allowed us to further reduce the uplink one-way latency by another TDD period, so another 2 milliseconds, leaving the improvement to 4 milliseconds. In this slide, I've collected all the measurements that I've shown, and I can tell you that we had almost 40% of improvement in the downlink one-way latency and over 50% improvement in the uplink one-way latency. So this was it for the evaluation. Now let me tell you about the future steps of this work. As I said, the USB-based interface between SDR and host computer introduced a non-negligible amount of latency, more than 250 microseconds to be specific. For this, we are looking at PCIe-based software-defined radio. Namely, we are looking at Lime SDR and the Android Digital M.2 SDR to exploit their direct memory access feature to exchange samples from the host and the SDR quicker. Let me also tell you about the limitations of this work. So, reducing the H and M slot offset, which allowed us to reduce the latency, is very hardware dependent. So the values that we have found to work on our setup were very dependent on the CPU that we had and the SDR that we used. So probably running such a competitive H and M slots of offset on a Raspberry Pi probably would not work. Moreover, these H and M slots of offset are also dependent on the numerology. So all of the values that I've given here today were focused on numerology 1. Moreover, and that was for our first 2 modifications. For our third modification, the one in which introduced the scheduling request free access mode, one has to be very careful about allowing this constant uplink grant, because they can be very wasteful. Like if the UE did not ask in advance, this uplink grant can also go unused. Moreover, it's also very hard to see this scaling, because you can do it for 1, 2, or a couple of UEs, but probably not for tens or hundreds. Furthermore, this analysis was done on a very specific band with a specific numerology and a very specific TDD pattern. So all of these values are going to change if you change the TDD pattern or the numerology. In fact, I was very happy to see in the SRS roadmap that they were going to support numerology 2, because we believe this is going to make quite an improvement in the latency by shortening the slot time. And to address the last limitation, I would like to point out that my group has worked on a more comprehensive latency analysis, which did not only focus on SRS, but it was a more general analysis of the latency in 5G, and which is going to be part of a future publication that is going to come out next month at Hotness. So in this work, my colleagues have looked at all sorts of TDD patterns at FTD configurations, and they follow the packets throughout the entirety of the stack, so both on the G-Node-B side and the UE side. They have a journey of a ping packets throughout the whole stack, and they measure the latencies throughout all the layers. And speaking of, in general, of my group and publication, we also have another publication that is coming up, also at Hotness in the next month, in which we have tried to integrate WebAssembly in the 5G RAN stack. So for those who don't know WebAssembly, it is a portable bytecode, which is a compilation target for many high-level languages like C, C++, Rust, or even Python. It has a few nice features, like being hardware and operating system agnostic. So one can create a plugin, compile a plugin, and execute it in very different hardwares. So across maybe one has different deployments, and using WebAssembly enables you to run the same bytecode across all platforms. We have used WebAssembly in mainly 2 areas of the of the stack. First, we implemented a two-level scheduler to support for slicing within the SRS code base, with a first level of scheduler that decided among assigned the resources among slices, and a second level that assigned resources to UEs subscribed to a slice. And we allowed the second layer to be executed as a plugin, so allowing a slice owner to be in charge of its own scheduler, and also it allowed the slice owner to change the scheduler during runtime without having to recompile the entirety of the stack. Moreover, we also used these WebAssembly plugins to try to solve one of the ORAN integration problems. So we know that there exist these interfaces that are supposed to be standard and just be intercompatible, but we know that it usually requires quite a bit of work to actually make these components work together. So we envisioned running WebAssembly plugins within sandboxes in both sides of the ORAN components in order to allow developers to just execute their own code on both sides, allowing better integration between components. That would be it. I would be happy to take any question. Yes? Yes. We use the Boost accumulators. So this is a library that is available in C++, who makes some quantile, it collects an amount of runs, and it computes like the 50th, 75th, 99th percentile of the latency. So I believe in here we reported the 99th percentile. So Boost accumulators is what we used. Yes. I believe that, I believe they are very susceptible to high and low loads. So whenever you have a lot of data through transmission, the queues are going to fill a lot. And whenever you don't have a lot of data to transmit, this value is going to be very low. So I believe that's the reason why the standard deviation is high. Yes?
I just want to say thank you for this presentation. It was very detailed.
Yeah.
I'm the one who did the lower file, so when I saw your labs, I felt like, oh, this now or this is not.
Sorry. Could you repeat it? I couldn't hear you.
Oh, thank you. I did a good work explaining how it works. It's really complex, and I tried to draw it many times.
Yeah, I mean, the matter is very complex, so I tried my best to summarize it in a very short talk, but it wasn't easy. Like you worked on this stuff, right? So you know how complex and how hard it is to summarize.
Yeah, it is very complex, it's hard, so thank you for your work.
I want to say one last thing is this work is mainly due to one of my friends, OU, that unfortunately wasn't able to come here and present it for himself because he couldn't get a visa. But if you want to read more about this, he has a very nice thesis. He wrote his master thesis on this, and I would be very happy to send it to you, so just contact me.
Okay, do we have any more questions for Raphael? No? Okay, great. Raphael, thank you so much.
Thank you for having me.